Thank you for joining us for this live stream on Graph Network. I'm Charles Pooh, one of the developers of Graph Network. And today I want to give you my inside view of Graph Network, both on the design side as well as an implementation, and hopefully cover some applications. This talk will be essentially divided in two parts, a modeling aspect of Graph and the analysis aspect of Graph. By modeling, I mean, if you take a real-world network, like a road network, you want to be able to represent it as a graph, the actual model. And from that model, you should be able to do actually the analysis, compute property. And at the end, you get a result which you can synthesize and interpret and bring back to your world and have a real meaning to it. And that's pretty much the way all the functionality in the system is built, so around modeling and analysis. So before that, let's just, get the basic on graph networks, right? So from a sample view or a graphical view, if you want, a graph is just a collection of points which are joined together by lines, right? And those points, you call them vertices and edges, right? And in this example, you see actually a basic graph. This is a Peterson graph with 10 vertices and 15 edges. So graphically, you see a nice network connections. And in different areas, people have different names, right? So if you do social network analysis, right, you look at, social interaction between actors. So your vertices are actors, your edges are the interactions. And in some cases, we call them node, and in some other, you call, vertex node, and you call the edge links, right? And if you do a polynomial network or other thing, you have different type of names. So for me, pretty much, when you have a network, a real thing which have a structure and a behavior, I tend to call it a network. And when you look at the model, the math aspect of it is what I call graph during this talk. So hopefully that will kind of make the distinction between the network and the graph. So in the Wolfram language, how do we actually represent the graph? So we represent the graph by a symbolic expression, which is, with a head graph. After that, you have a list of edges, right? So to describe the edges, we have two types, undirected edge and directed edge. So the undirected edge, you just type undirected edge, U and V. So this will typeset and represent the edge between U and V. So this is a basic example where you evaluate the graph, which have in this case 6 edges, and you get the graph. Right? As I mentioned, we also have directed edge, which is the second type, where you have actually a connection between U and V. So you actually give a direction and the way they are actually connected. And the syntax is identical to the undirected edge when you give it to graph, and you just have to, write directed edge instead of undirected edge. Right? So then you get also an undirected edge graph, which is quite simple. And so one thing you notice actually from this is that every time you actually give your graph, it actually auto-visualize, right? Instead of returning a symbolic expression. This is actually a pretty good feature of the system, so you directly see actually the structure of your graph. And behind the scene, we automatically try to find out what is the best way to actually display that graph. And obviously, if the graphs get too big, right, we have a limited amount of space on the screen, right? What we do, we return that symbolic representations, right? And so if you want to see it, one first thing you can do is you can actually change the system option. So we kind of limited the auto visualization of the graph to a graph with vertex count less than 1,000. So if the graph have less than 1,000 vertices or 10,000 edges. So you can take the system option and modify it if you want. As well as the system option also have cache result if you use the system cache, where we actually automatically cache the result of the computation or the auto visualization of the graph, the vertex coordinate and such. But Another easy way, if you just want to visualize your graph, is to use graph plot, right? So in this case, you see that graph, which, well, a similar graph with 10,000 edges and 1,000 vertices. It actually automatically rendered with graph plot, right? So it's kind of a dense graph. And one key difference with graph plot and graph in terms of visualization is that graph return an actual object graph and graph plot return a graphics, right? So this per se, this object is not computable, but you can manipulate it with, for example, show and combine graph, right? So if you take a graph and put it in show, you can manipulate it as a graphic expression. So that's kind of an advantage of having show or having graph plot when you want to actually manipulate them or visualize graph and just merge them and combine them. So the next thing I want to highlight essentially is that graph is actually a whole object in the Wolfram language. So that means it's atomic. So you cannot per se go and take the first part. You can ask the head, obviously, we return you the head, which is graph, but you cannot actually go and take part. So what we did is that we introduced a set of functions or a structure function to actually allow you to manipulate the graph. So in this case, I take generate the complete graph, right? You can check that is a graph queue, by graph queue, or you can check that is undirected. So we have all those queue functions for you to use. But you cannot really take the first part. So if I evaluate it, part tell you, oh, it's an atomic expression, I cannot go inside. But you have vertex list, which return you the list of vertices, and edge list, which return you the list of edges, right? So those are kind of the two accessor functions. Well, we also have actually options. Which will return you the option of the graph. So in this case, the graph doesn't have any options. And what you can actually also notice here is that you can actually take that graphical representation of a graph when you're in a notebook and just put it in your function and evaluate it, right? The front end automatically interprets it as a graph and the appropriate computation happen. So there's all those flexibility around the graph object, which kind of make it look nice and alive in the system. So before we continue, one key thing I want to highlight is that, the way you specify and you construct the graph affect actually the subsequent computations. So in this example, I just have pretty much two identical graphs where I just essentially permit the first and second edges. So here I have a 1, 2, 2 to 3, 3 to 1, and 1 to 4. So I flip them here. So the first thing you notice is that when we render them, the visualization is different, right? And one key thing is that when we actually look at this graph and build it, right, we actually collect the edges. So implicitly, the list of edges between these two graphs are different. So if I evaluate them here, you see that the vertex list is 1, 2, 3, 4 for the first one. And the second one is 2, 3, 1, 4. So the vertices are collected in the order of they appear, and that actually affects the subsequent operations. For example, the adjacency matrix, right, which represent the connectivity of your graph, right, essentially is based on the order of the appearance of your vertices. So the first graph, you have 1, 2, 3, 4, and the same for the column. And the second graph, you have 2, 3, 1, 4. 2, 3, 1, 4, and then you see that the two matrices are actually different, right? So the way you actually build the graph actually affects, subsequent operations, even though visually they may be similar, or mathematically the way you actually express them are quite identical. And that's why we have operations such as graph isomorphism to check if the two graphs are actually equivalent, if there is a mapping which actually preserves the connectivity for the two graphs. So this is kind of one important feature, which in some cases you may be confused why your result may be completely different, right? Just make sure to check your vertex list or the ordering of the vertices as you specify the graph, right? And one way, if you want to make sure that everything is exactly identical, you can actually specify the order of the vertices this way. Right? And obviously the order of the edges will be different, but you see that the rendering actually got consistent here. And the adjacency matrix will are actually identical in this case. Right? So this is kind of one thing to keep in mind when you construct your graph and you want the subsequent operation to be consistent. Okay. Earlier, I kind of talked about matrices, and let's look actually at the representation of matrices here. So an adjacency matrix, right, just represent the connectivity of your graph. So we have adjacency graph to actually build your graph based on the adjacency matrix. And you can actually also extract it back with adjacency graph. As you see here, adjacency graph return you a sparse array, which you can actually use matrix to see actually the structure. We tend to return a sparse array because most of the graph we have are not dense. So that's sparse enough. So sparse array is an efficient representation for sparse matrices, right? And also subsequent operation actually take advantage of that structure, that sparsity of your matrices. So this kind of brings us to actually the internal representation of graph, right? And obviously the graph, in Mathematica is actually a data structure, and we want to actually have that data structure to be efficient in terms of computation as well as in terms of storage. And the way you build the graph actually affect that, as we saw first in the adjacency matrix and vertex list, but it also affects the way we actually keep it and store it. So when you build a graph with just a list of edges, by default, we store it as a double link list. So essentially, we link the vertices and we link the edges together, right? And in the perfect world, you have actually a compact representation in memory where you can actually do the appropriate jump and connections together. Right? But if you give a graph with a matrix and you build it with adjacency matrix, what we do internally is that we actually store the adjacency matrix. So instead of building a double linked list, we actually just store the matrix and we operate with that. And most of the algorithm, when we are going to get to the analysis part, actually take advantage of those structure, and we have implementation specific for each structure. One way to actually see, what actually present here is actually by looking at the full form of your graph, right? Which is close to the serialization we actually do in memory or also kind of in files. So in this case, when you generate the graph and you ask the full form, you see that you have the list of vertices here, and then you have the list of edges. Right? But when you do the same with a adjacency graph, you have the list of vertices, but here you actually have the structure, the sparse array, which we store internally. So that kind of will give you an idea of which structure we are using inside. And what type of operation may be more efficient when you do you construct your graph with a sparse array, or you construct your graph with a double linked list. Okay. Okay, so before we jump to the analysis, but let's just kind of go to the list of type of graph we have. So obviously we have undirected graph, and here I'm just using the edge list to specify them. We have directed graph, and you see the arrow automatically appearing in the rendering. But we also support mixed graph, where you can actually give both a directed edge and undirected edge. And automatically we represent it as appropriately store the right information. And down here, you can actually also see that we have multi-graph after the mixed graph. So where you can have parallel edges, so which connect actually these two vertices in between. So those are kind of this, the graph coming from, structure or modification of your edges, essentially. But there is also other type of graph you can actually build by adding additional information, right? So the first type is, weighted graph. So in this case, you just, have your graph, but you can actually add a weight to your edges. And it's also to your vertices in general, but most of the time people just add weight to edges. You can reconstruct the original matrix or the weighted adjacency matrix for your graph. And you can do operation on them. So several of the type of operation we have actually take into account the weight. So for example, if you are computing a distance for your graph, we take into account if it's weighted or not, right? And we have different functions for that. So conversely, you can also have the matrix and build your graph. So we have weighted adjacency graph. So there you have the corresponding graph from the weighted adjacency matrix. And weighted adjacency matrix can show you exactly that. So one thing you will notice here is that the original matrix, right, have infinity as a way to specify that there is no connectivity. And when we return the weighted adjacency matrix, we actually specified with a 0, right? So this is more a design decision we pick at the time. So when you build a graph, right, you have to kind of, especially when you have weight, you have to pick the value which signifies, mean that there is no connection between, two vertices. So what that value can be. In the case of weighted adjacency graph, we went with the decision that infinity means there is no connection. So similar to when you generate a graph distance matrix, right? When two vertices are not connected, the distance is infinite, right? Which is slightly different than the adjacency matrix when, where if there is no connectivity, essentially, you say there is a value 0 between the two vertices, right? So that's kind of slightly confusing, but what you can do in general is that when you build a weighted adjacency matrix, you can actually specify, the second or the last argument of the function. You can actually specify the default value, and it will take that into account. So in this case, you say the default value is 0, and there it builds actually your matrix. Okay, so that's kind of one view of the weighted graph. The next type of graph I want to talk about are the edge-tagged graph, right? And this essentially comes from the fact that when you have a graph with parallel edges, a multi-graph, right? So it's hard to actually distinguish, the two different edges which have the same, vertices, two edges have the same vertices. This is an example here. So let's just if I evaluate that graph, so I have two edges here, 1, 2, 1, 2, 2, 3, 3, 1, right? And you see that when you essentially say, okay, I want to color the vertex 1, 2 into red, we pass it, we cannot really make the distinction between the two vertices, and we color them in red, right? So edge tag actually allow you to avoid that and actually add an additional tag or kind of a descriptor to every vertices in your graph, right? And what we actually did is that we extended undirected edge to actually support tag. So the third argument of your directed edge and undirected edge are tags, right? So in this case, you generate a graph with tags, so visually nothing really changed, but internally there is a tag which is associated to every edges, in this case, A, B, C, D. And if you actually use edge tags, so in the earlier example, you see that we have graph couldn't actually, distinguish the two, but in this case, edge tag is actually able to distinguish both. This one is drawn with red, and this one is blue. So edge tag is actually what you want if you want to play with, multi-graph and make sure that you can actually distinguish or pinpoint every edges which are parallel. Okay, So the next more interesting part also in graph is the annotations, right? So in the language, expression in general, you might have a form, head, argument, followed by options, right? But graph is actually an object, right? So one is that we want to be able to modify it, right? And essentially add more property. So what we introduce essentially is the concept of annotations, where you can actually take your graph and annotate every part of your graph. You can annotate the vertex, you can annotate the edge. And what we did is that, we introduced what we call the standard annotation, which map exactly to option in your system, right? In every expressions. So in this case, you have a graph, and this is a set of options you add, which are kind of considered as, standard annotations. So if you evaluate your graph, you will get, that, right? And if you actually use wrapper, and you saw an example earlier, what we essentially do is that we take that and map it back into annotations, right? So everything in the system, when you get out of the topological structure of your graph, right, just directly map into annotation. And that's the way we actually store all the information you actually add to your graph, right? An annotation actually allows you to make that link from a network, real world object, which have a behavior, to the abstract graph, right? Which have both the mathematical topological structure as well as additional metadata you want to manipulate. So this was an example of the spatial wrapper. And here there is this is an example of a user-defined annotation. So you can add your own annotation to the whole graph, obviously, to vertex and edges. So in this case, I add annotation to the edge 1, 3. So I get my graph. So let me call that graph G. And I can obviously take that graph and say, okay, what is the annotation value associated to the edge 1 to 3? And you get there, you get the strength, and it's 10. And you can obviously take it back, manipulate it. In some case, some algorithm will actually use it automatically. Okay, so that was kind of a view of the fundamental object we have, graph, and the different behavior, and hopefully kind of give you an idea of the implementation and structure we have behind. So let's move now to the modeling part. As I pointed out, right, all our functionality pretty much resolved from those two aspects, modeling and analysis, right? So modeling allows you to actually take the data you have in the real world and build the abstract model, the graph in the system. So this is kind of the different type of model you can find from computer science, physics, economy, and such. So those are different type of graphs. So I won't spend time on this. So let's suppose you have some data. In this case, this is a social network from the /dot, which is, technology website. So you can use import to actually import that data. This is a purely test file. And you can actually just take that and restructure your data to generate a graph. And there we go. You have a graph which have about 100,000 edges and such for vertices. Right. So one way to actually build graph or model graph in the system is by using import and export, where you can actually take those files depending on your, the structure of the data, and build the graph out of it. But we also support, standard graph format, graphlet, dot, graphml, GXL, and such. So you can just directly import those type of files, as well as export them and generate those type of files. The next type of collection of data or empirical type of graph we have are theoretical and empirical graph, right? So if you are more mathematically inclined, right, there is a set of standard graph you are used to, right? So graph data is a vast collection of those type of graph. I think it contains about more than 6,000 standard graph as well as property. So you can just use graph data and give the name of your graph. There is downloading the data from our server remotely. and you get the graph, and you can start directly to work with it. We also build a collection of empirical graphs, which are most common when you do social network analysis, for example. So this is kind of the connection of the Florentine family, right? And you can take that graph and directly manipulate it. So what we try to do is to provide you, both with empirical graph and theoretical ones, so you can easily start to play with graphs. So the other set of way people actually build graph are from, distributions, right? Similar to when you do probability and statistic. So one standard mode, standard type of models for graph is the Remy models, which is a uniform distribution of graphs. So we introduce random graph, as well as a bunch of distribution, I think about 1, 2, 3, 4, 5, 6 of them, which allow you to actually generate those models, right? So here you have random graph, generate a uniform graph. So if you keep evaluating it as any other function, it will generate you different type of graphs, right? So we also have the Gilbert model, which is based on the Bernoulli graph distributions. And we have the degree graph distributions, right? So you can essentially generate different type of graph and do your analysis on it. One interesting thing we added is graph property distribution. It kind of allows you to actually make the jump from those graph distribution to actually standard graph in statistic, which essentially map to a value, right? So this is an example where you take, graph property distribution and you try to look at the edge count of those type of graph. And, there you specify that your variable G follow the Bernoulli graph distributions. So if you evaluate it, it tells you actually what is the distribution of the edge count. So the number of edges, what follow the distribution. So for a Bernoulli graph, the distribution of edges follow a binomial with some specific parameters, right? And obviously, for this type of graph, you can, get this type of closed form, but in general, it's not possible. So this is an example where you look at the Stroboscan distribution from a small world network and try to look at the clustering coefficients, right? Obviously, there is no closed form for that, but you can still use random variate and get actually the value. So in this case, I do even a 100 of them. So what behind we do essentially, we have different Monte Carlo method to do the right simulation and return you, random variate, where you can actually, right now take it and study that distributions. So, and that's kind of quite interesting. As I say, graph property distribution make you that bridge to the probability and statistic. We also build several similar bridge, right, to different other areas in the system, right? So if you do linear algebra, and obviously graph is connected to linear algebra, and I talked about it earlier, adjacency matrix. You can take your matrix and call adjacency graph to build a graph. So from linear algebra, you can actually jump into graph. And if you actually analyze, do some complex computation in linear algebra and want to look at, graph structure of your matrix, you can actually use adjacency graph. You can also take your image and use morphological graph to actually build your graph. Or if you do geometry, you can call mesh connectivity graph, like you see in this case, and get your connectivity of your graph. Or if you do chemistry, you can call molecular graph to actually build the graph out of it. So we try to build different bridges between different areas. So you can actually use graph and network as a tool to actually work and do some analysis of in your area. Okay, one topic I will probably just, go really fast, and my colleague J-Bomb will give a talk next Wednesday at 11 a.m. Central Time, will be on graph visualizations, right? As I showed earlier, we auto visualized our graph. And since it's in the notebook, you actually get all the features of the notebook. Like in this case, you can get, mouse over, tooltip, and so on. So I won't go into detail with that. JBOM will present all the nice feature we have for graph visualizations. But what I will just kind of highlight is that, what we have been trying to do is also to add more high-level function for your graph layout, right? Because behind the scene, we have several types of layout, right? But, they need different parameterization and, value so that you get a nice, nice looking graph at the end. Right? So what we have been doing is introducing different type of functions. Graph plot will kind of generate your graph in 2D, graph plot 3D in 3D. Tree plot will identify if it's a tree and generate the right layout. Layer graph plot will essentially put your graph in different layers based on a topological ordering and connectivity. Community graph plot will take your graph and connect them based on the community structure and other modularity parameter for your graph. And obviously, graph embedding gives you the general value of your graph in the space. So we have a set of function or plot function to actually allow you to handle your graph properly. So JBOM will talk about it more in details and show you really nice graphics and rendering for that. Okay, so that was kind of my view about modeling, right? And the different way we have actually for you to actually model a graph, right? So now let's talk about analysis of a graph. So one is that we have a set of functions to analyze or provide structural property of your graph, right? So there's basic property, vertex count, edge count. But now you can look at the topological structure, right? Is it directed, undirected? Is it simple, or does it have loops or multiple edges? And after you move from it, you can look at more complex structure, right? Are these two graphs identical, even if I apply some rotation or a mapping? So it comes with isomorphism, right, there. Or if you want to detect, is there a cycle, right? Do they have what's the connectivity of your graph? We have connected graph queue and such. So those are kind of the structural operations and functions we have. And now when you move a little bit far away from those basic structural operations, you can start to add more advanced questions, right? Can I find the path between two different vertices? Or can I find a cycle, a Hamiltonian cycle, so that I can traverse all the vertices in a certain way, right? So we have Eulerian, find the Eulerian cycle, find the Hamiltonian cycle, and a bunch of other functions to actually analyze your graph, find shortest tour, find Postman tour and such. And just for the fun of it, this is kind of a nice example. We'll show how you can solve a maze using the graph functionality, using those cycle operations. So this is just parameter to style your maze, right? So we generate the maze as a grid graph, right? And one of the easiest way to generate a maze is to use spanning tree, right? So you generate the spanning tree, and there you have a maze. And you can use find shortest path to find the actual path and solve your maze. So I run that, and you see that directly here, you have the path. So the functionality is quite nice, both visually and graphically, so that you can take it visually nice, see your graph, manipulate it, or analyze it. So the other next set of operations we have are centrality, right? Everybody know the PageRank centrality, which was kind of the base of the Google PageRank. But we also have closeness centrality, betweenness centrality, class centrality, eigenvalue centrality, which each one gives an interesting property of your graph, where essentially you want to give a value of importance for each vertices or edges in your graph, right? So this is an example of the Florentine family, right? As you know, the Medici family kind of rose to power. And, it's always interesting to know how was it possible, right? They were not really the richest family there, but you can see that through marriage and connection, they kind of, have a central position in all the network in that society, the Florentine society at the time. And that's why they were really powerful and really involved in politics in Florence at the time. I will reuse this example in my talk in 2 weeks, where I will give a talk on social network analysis, and we probably kind of dig more inside and look at those centrality functions and how they are useful to analyze social network. Another set of functionality we have are connected component, connectivity and connected component and related object, right? So connected component give you the set of vertices which are connected together. So essentially you can move from one to another one. So there is a path between them, right? So this is an example which was similar to what I used earlier, the /dot connectivity. So here I kind of do a quick analysis of the connectivity of the graph. You can get the number of graphs, you can get the size of the largest connected component, right? The number of vertices, the node, and you can even analyze the clustering coefficient. Or you can actually take the number of in degree or odd degree of your network and actually see if it follows a known probability. In this case, does it actually follow the Pareto distributions? Or does it fit in this type of, graph with a certain type of property? So you can easily kind of do that with, just a few comments. Okay, so what I try to show here is one is that, the graph object in the system is quite simple and work naturally in both the front end and behind the scene as you want to do analysis. And I try to show the two modes of modeling analysis for graph, as well as just slightly talk about the visualization, right? So I hope that kind of gives you an idea of the functionality in the system. And in probably the next couple of talks, we'll kind of go more deeply and talk about different aspects of algorithm. So that's pretty much all what I have today. I will take a couple of your questions if there is any on the chat before we close up here. Okay, so I don't see any question on the chat. I hope this kind of gave you an idea of the functionality. So if you have any question, feel free to post it on the comment of the different video, and we'll try our best to answer them. And join us next week in JBOM talk on graph visualization, and my talk 2 weeks from now on social network analysis. Thank you.